Hello everyone. Welcome to another exciting chapter of Crystal Clear Electronics 2. As you might have guessed from the video title, in this couple of videos we'll be talking about ADCs or analog to digital converters. The presenter of this chapter will be Daniel Pivko, who you may have met in several videos before.
That's right. Hi everybody, it's great to be back, and thanks to Zola and Jurica for helping me with the videos of this chapter. Both Zola and I are currently studying for our Masters in Electrical Engineering, so we have experienced firsthand how important and relevant the chapters of the curriculum are. For example, this chapter is particularly close to us because as part of a joint university project, we have to perform approximately 70 analog to digital conversions simultaneously, and we can use the results to implement the control of a model car.
That's right. In this chapter, we will get familiar with the analog to digital converter of the STM32 microcontroller. First, we'll take a broad look at what you need to know about the ADC, then we'll learn about the configuration options of the ADC module of the controller on the development board, and then we'll learn how to use it through interesting exercises.
If you haven't heard much about analog to digital converters, or ADCs, we suggest you look at Chapter 22 of Crystal Clear Electronics 1, where they are discussed more broadly.
Chapter 11 was written by Máté Trádler and proofread by Tamás Horváth. Let's get started. First, let's look at when we need to use an ADC. What does it exactly do?
We can measure a wide range of analog signals: temperature, distance, luminosity, voltage, current, and many more, but we need to convert all of them into a voltage first so that the ADC can process them. This conversion is done by sensors, which you will hear more about in Chapter 13. Another good and practical example is to measure the voltage of the power supplies on circuits, as this is a way to make sure they are working properly and we can intervene in case of a fault. For example, if we can detect a drop in battery voltage, we can save the data we don't want to lose in the case of a power loss to a non-volatile memory before the battery runs down.
The voltage to be measured is an analog signal, that is, it has a well-defined value at each instant of time and can take an infinite number of different values. In contrast, a digital signal changes its value only at given intervals, and it can only take fixed values, therefore it is called a quantized signal. A good example of such digital signal is a clock signal, which changes its value at fixed intervals, every half period, between two well-defined voltage levels.
Microprocessors can only and exclusively process digital signals. Continuous signals must be converted into digital signals to be interpreted. Perhaps the following four figures will help you better understand. The top left figure shows an example of the analog signal. After the so-called quantization of the signal, we have the result of the black line in the upper right figure. In this case, the received signal cannot take any value, but we must trace the original signal to the best possible extent with defined signal levels. It can be accomplished if the converted signal always takes the quantized value closest to the original signal. This is why, in this case, we see the black line as a stepped curve and not a continuous curve as in the case of the original signal. The bottom left figure is what we get when we discretize our original signal. In simple terms, in this case, we take the current value of the signal at certain intervals, measure it, read it, and use this signal value as a basis until the next sampling. In the case where we apply both of the two transformations to the original signal, we get the result shown in the bottom right figure. In fact, what happens is that the value of the signal is measured periodically, and the measured value is rounded down or up to the closest quantized value. In a very simplified way, this is how ADCs work.
The continuous signal will be described by a sequence of binary numbers of a certain length, and the necessary conversion will be done for us by the analog to digital converter. Unfortunately, as with everything, ADCs have their limitations.
Unfortunately, they do. Since we want to map an array of infinitely many values into an array of finite numbers, information loss is inevitable. The analog to digital conversion can be characterized by its resolution, which is the total number of different values that a discrete signal can take. We express this value as a power of 2 because we represent the converted values with bits in binary form. For example, suppose an AD converter has a resolution of 10 bits. In this case, 2 to the 10th power, that is 1024 different values, can be produced at its output, with a maximum value of 1023 and a minimum of 0. However, it makes a difference whether we use this resolution between 0 and 230 volts or between 0 and 1 volt. The full scale is used to characterize this. This is the range of the input voltage within which the output is a linear function of the input. If a signal is applied to the input that falls outside the range, saturation can be observed, whereby the ADC cannot produce a high enough output. In such a case, even if the input voltage is increased, the output will only be at its maximum, or conversely, even if the input voltage is decreased, the converter will not produce a digital output less than 0.
In extreme cases, the ADC may fail if the input range is not respected. Usually this range starts at 0 volts and ends at the reference voltage of the ADC.
The metric that expresses the ratio of the input range to the resolution is called LSB, which stands for least significant bit. Its dimension is voltage and tells us, and now listen to me, how much input difference there is between the corresponding voltage levels of two adjacent output binary values. If you understood it the first time, then hats off, but in simpler terms, for an LSB increase in input voltage, the output binary number will increase by 1 in the ideal case. Multiplying the given binary value by the LSB gives the measured voltage value. It's important to note that this does not tell us what the voltage level was at the input, but what the binary value represents. The difference is due to the quantization mentioned earlier. This figure illustrates what has just been said. It can be seen that the ADC samples the blue input signal at each vertical line and adjusts the red output signal to be as close as possible to the measured value. It can also be seen that if the input signal exceeds the full scale level mentioned above, the ADC will then return the highest binary value it can output to us. Unfortunately, it's also easy to see that the samples taken from the continuous signal do not describe the original signal correctly. This is, of course, a nuanced expression, since it's always up to the designer to determine the error below which the original signal is considered correct. In the present case, the conversion is not shape-preserving, since the signal changes faster than we sample it.
Luckily, there is a solution to this problem. To improve this, we need to sample the signal more often, that is, increase the frequency of our sampling, so that we can describe the input signal more accurately.
Just as you say, let's look at our previous signal at a higher sampling frequency. You can see that increasing the frequency gives a better representation of the analog signal than the digital signal in the previous case, since the faster changes are also reflected in the digital signal.
This was the key information about ADCs. If you are interested in more details, please read the written version of the curriculum on the website.
And also, stay tuned for the next part, where we will take a look at the AD converter of an STM32F4 microcontroller.
Bye.
Bye!